Good morning. Last day of DEVCON, so I'm hoping that you guys will enjoy this lecture. So this is the microcontrollers enabling safer designs. My name is Nelson Quintana. I have been involved in the embedded space, specifically microcontrollers, for over 15 years, and in different areas, including application engineering and more recently marketing. I have been quite involved in the product definition for different application segments, and I've worked closely with design team to develop products with specific features geared towards safety standards. In particularly for some of the markets such as household appliances and more recently factory automation. I will be focusing in the microcontroller area, and I have a few examples to illustrate using the RX and RL78 microcontroller families. So how does safety play a role into this whole enabling of the smart society? So you can imagine, if you look at different markets, different applications, we're starting to see more and more of a trend in the increase of safety requirements in different applications. So yes, you have your factory automation. Some of the specs there include the 61508 from IEC. In appliance space, there are some specs or some standards there, but you're starting to see that more and more being applied to other segments. So it's definitely a trend. And because of that, you as a designer, you have to take all those requirements into consideration when you are designing your systems. I came across this interesting graphic that talks about safety excellence, and talks about some of the elements within the safety, which I want to highlight just a couple of them. Obviously, to mitigate the risk, technology is one of those aspects that is playing a very important role. So this course is going to be focusing on, as I said, MCUs and how MCUs can take advantage, or how you as a designer can take advantage of the MCU's functionality and flexibility to address some of these safety requirements. I'll go over an introduction of safety. Then I'll move on to how we can utilize some of the features in the microcontrollers for safety compliance. And then I'll move on to what Renesas is doing today and the direction that we're taking in terms of integrating more functionality into the MCUs to address safety requirements. So introduction to safety. So safety or functional safety is part of the overall safety of the system. Is actually part of the overall safety that depends on an active system to operate correctly depending on its input or the way that it's utilized in the overall system. A functional safety design has to, its main function obviously is to detect the dangerous conditions and mitigate or correct those conditions through different mechanisms. One very important thing to remember, and I'm sure a lot of you who are doing safety designs today are aware of this, the safety is really an end-to-end scope. It's not just a component, it's not just a subsystem, it's really the big picture. So why are we talking about safety? Why is safety important? So from a very high level, safety is very tightly coupled to productivity in many of the industries. There's a study done back in 2009 that estimates that over 70 billion is actually lost in productivity due to safety reasons. Probably from your standpoint, designing for safety, in some of the industries, obviously, it is a requirement. There are standards that are there. And if there are not standards out there that are enforced, you probably do want to take into account safety mechanisms to make your products more reliable for consumer consumption. From a corporation standpoint, obviously, companies do advertise that, hey, you know, I have a safe environment. They use that. It does reduce the cost of operation, I say, in a factory environment. And again, from a product standpoint, a product development standpoint, one of the benefits, obviously, is if the product is designed for safety and reliability, you will probably get fewer product recalls, which will impact your overall cost. Now, the other aspect, which is probably more relevant to the discussion today, is software, the use of software control in a lot of these systems. So more and more systems are utilizing programmable devices, MCUs, and so on. And as you probably all know, testing some of these systems, testing your software, making sure that the software is reliable, is not an easy task. So the reason why there are some of these mandates, some of these regulations and standards that are being either enhanced or even enforced in different markets, is to ensure that whatever system is designed today that uses a programmable controller goes through some sort of certification. So taking a look at safety from a system view, as I mentioned before. So safety, I say, is end-to-end scope. It's not just processes, it's a machine, it goes down to the system and component level. It is very important, you as a designer, that when you look at your design and you design for safety requirements, that you select the right feature set, at least options to enable you to design those systems with safety in mind in terms of features and capability. From a safety or risk reduction or risk mitigation, here's just an illustration of typical flow. And again, a lot of these concepts, I'm trying to narrow down. I'm trying to give you first of all a big picture. This is common across different applications. Here's a flow. The three main elements, obviously, is your risk analysis, risk assessment or evaluation, and then all your risk mitigation techniques that are utilized. And of course, this is an iterative process. If we talk about risk analysis a little bit, there are many methodologies, techniques to do that. You can imagine, in this case, a motor control system. You have different blocks within the system. You have a controller, the power stage, your motor, power supply, a lot of interconnectivity, a lot of different variables. So a lot of things can go wrong. So there's obviously a lot of techniques that designers already use today to do your risk analysis and risk mitigation. FMEA is one of those that is commonly used by many industries. Very good method to detect single point, discrete failures. And one of the things that I also want you to walk away with is that all of the standards that are out there, doesn't matter which application it is, they're very vague, right? They don't tell you exactly how to mitigate the risk, right? They tell you these are the requirements, this is what you have to take care of, but they don't tell you how to implement it. However, there are some specs, such as the 60730 for household appliances, which I will talk a little bit more in detail later on, which does give some recommendations which are relevant or related to microcontroller characteristics or features. So, as I've mentioned some of this before, there are different standards for different applications. You have your industrial space with the 61508. automotive, ISO 26262. I'm not sure if anybody joined yesterday's session from the automotive team. They did have a session talking about that and what Renesas is doing. Medical, 6061. This is the overall medical safety compliance. And by the way, there's a lot of complexity even within the standards. There's a lot of connections. You have software aspects, which are perhaps even different standards that all play into this. And then you have IEC UL 60730. Okay, so moving on to some of the examples of how we can take advantage of microcontroller features for these safety requirements, and I'll be using the 60730 as an example. Before I do that, though, let me just take a look at some of the considerations that need to be taken when you have to design for safety. So in the past, when safety wasn't of concern or it wasn't required by some sort of a regulation, you had a controller, and all you have to worry about was, that controller to do its whatever function it had to do. With now the safety requirements coming into the systems, you have to think about how you will address those safety needs within the microcontroller itself. So you may have two functions within the microcontroller to address your standard operation and your safety requirements. In some systems, you may be required to use redundant MCUs, which is actually out of the scope of this session. Very important to remember also that even within one spec, standard safety spec, the way that the safety is implemented, it depends on the application itself. So there is no one recipe to say if I have an oven and a refrigerator and a dishwasher, I'll be able to do my self-testing in the same way, because every system is different. You may be using different resources from the MCU. So yes, there are some commonality, there's some standard stuff, and I'll show you later on some examples of that. But let's keep that in mind that this is really more of an application-specific implementation. And then taking that system functionality into consideration, what a lot of the designers are doing today is that they are really treating this whole safety compliance capability built into the controllers as a modular approach, right? In fact, I mean it's done for various reasons: portability, modularity. You could reuse some of the stuff that you've done for one product for another product. So the modular approach is usually recommended. For some applications, it may not be feasible. You may have to work through the safety tightly integrated into your main controller. Okay, so let's talk about 60730 again as an example, and I'm not going to go into details about the specifications. I'm not here. I'm not the IEC or the UL spec expert. This is more to illustrate again what are some of the functions within the microcontroller that can be utilized for this. So here I have a block diagram, motor system. It could be anything else. You see there's a lot of blocks within the MCU that are utilized in this particular example. And the 60730 calls out 8 different requirements that are related to a controller. So we must be able to test for the CPU, for data integrity, interrupt handling, clocking, your data integrity for your ROM or flash, RAM, communications if you have multiple subsystems within a system. You want to make sure those are reliable. Your your input and output peripheral, and your analog peripherals as well. All of these things if they're being utilized in the system as part of, I'm sorry, if they're being utilized in the microcontroller as part of the system, there has to be a way to self-test or do testing for these blocks. Okay, so I'll go and give you examples of some of this. So let's take a look at the CPU. Again, the CPU is the brains, right, of your controller. So here's an example of a CPU architecture. You see the multiple registers, and essentially, what's required is that every one of these registers are to be tested for data integrity. Now, typically, I mean not typically, because this is at a very low level, architecture level, essentially there's only really one way of doing this. And the only way to test it is by writing test patterns in assembly. So you will find that you will find solutions available, including from Renesas, that are libraries written in assembly to do your test patterns for your CPU test. The other thing that the standard doesn't call out is when you need to do this self-check, self-testing. Again, it will go back to your system requirements. Depending on your system, what kind of functionality you have, you need to make that determination based on your risk analysis. But typically for a CPU test and others, this test is done at boot up, startup, and also periodically. Okay, second example is clock test. The requirement calls out to supervise or monitor your main system clock, whether your clock is operating or is not operating within the range that is being designed to do. Again, very simple mechanisms that have been used for many years. You can use external references, external clock references. You can have a 32 kilohertz. You can have perhaps a separate dedicated internal oscillator that can be used as a reference, or you can just use your external main supply to use it as a reference and compare it. Again, this is the recommendation that this is done periodically. And again, as Mark in the back just mentioned, a lot of this will impact, for sure will impact the design, right? Your timing, your scheduling, and that's the reason why when you have to comply to these requirements, you have to take all of that into consideration on how to architect the system. Okay, RAM, this is probably one of the most common ones, CRC, right? Again, some controllers have CRC engines, some don't. So, again, if he doesn't have it, all of that has to be in software. But the point is that the contents of ROM have to be tested periodically. RAM, similarly, there are many different algorithms out there already available in the industry that can test for RAM integrity. And here's an illustration of one of them. Essentially, example here is a MarchX algorithm that you can utilize. And again, depends on your application. You may decide that a destructive test or a non-destructive test could be utilized depending on your needs. Analog, peripheral, again, if you're utilizing, in the case of the motor control example, most likely the A to D converter is being utilized. That has to be tested, self-tested, when you're operating it. And a very simple example, probably what's been done in the past is use some sort of an external reference. There are other things nowadays that are available. You can have internal references, such as a VREF or a temperature sensor, and there are other things. You can also use interconnections. Say, for example, there may be a D2A available that you can use for your A to D testing and vice versa. So what are we doing in terms of safety? So let me start out with product level. Here's an example of an RX MCU called RX21A. It's a lot of integration. This is part of the RX family, 32-bit, a lot of functionality. But if we look at the safety aspect of it, there are multiple features that we have. So there's a CRC built in, register protection. You can protect your special function registers for the peripherals. Independent watchdog timer, which means there's a watchdog timer with an independent clock source. So sort of common stuff. What we have added on top of that is a memory protection unit, something that we call DOC, or Data Operating Circuit, and I'll explain what that is later on. A clock accuracy check circuit, and an ADC self-diagnostics feature. And again, I'll talk about those later on. For a lower-end MCU, this is an RL78G14. What we have is, again, there's a lot of stuff that I would consider more standard, right? RAM guard, which is sort of write protection, register write protection, invalid memory access detection, window watchdog timer, clock frequency check, and so on. In this device, what we are incorporating is actually a CRC that can be operated in two different modes, as a standard CRC or as a memory CRC, which is a higher speed CRC computation. And in addition to that, there are two features which are inherently there to support safety and reliability. One of them is a RAM parity error check correction, and an ECC. It's an ECC enabled flash memory. So talking about the DOC, I talked about it in the previous slides about one of the algorithms that's typically used for RAM test is MarchX. We do provide also, and I'll talk about that later on, we provide libraries, basically a software library for MarchX test. And if you look at some of those requirements in terms of ROM or timing, you're talking about half a K to a K of code space that's required for your MarchX test. And again, if you're talking about an 8 or a 16 kilobyte MCU, that's a big deal, right? So in this case, what we've done is we've incorporated this block to allow you to do all of your RAM testing. So the way it works is essentially you define whatever value that you want to have your RAM contents be compared. You bring the data in through a DMA engine, and all the comparison is done by the hardware, and then you get an interrupt, whether there's a match or no match. Actually, it has additional capabilities. You can do additional subtraction of the data. So again, this eliminates, it's not going to eliminate some of the software 100%, but it will definitely reduce the overhead in terms of software and timing. CRC is becoming more and more common in MCUs. They're starting to come down to the lower end MCUs. This is an example of the CRC in the RL78, which is a lower end MCU. We can operate the CRC in two different modes: standard mode for communication or any type of check, but also we can configure it for high-speed operation, and it's been designed to do CRC for ROM. Here I'm just giving you an example of how much time it would take, 512 microseconds, to do a full 64 kilobyte of a CRC calculation. As a comparison, if you do this in software for this type of a processor, it would take in the hundreds of milliseconds to do a 64K. Another hardware that we've built in that can take a reference clock, and it could be an internal clock or an external clock, and you can monitor your system clock. And again, it's not the typical or traditional way of doing it, which was, okay, let me use a timer, let me do all this calculation of whether I'm drifting or not. This is all done automatically in the hardware by detecting whether your accuracy, your clock frequency accuracy is where it needs to be. And there's different types of errors that can be generated out of this block. For analog to digital converter, I mentioned earlier, there again, it's becoming very common to have an internal reference voltage or a temperature sensor to use it as a self-testing mechanism to make sure that your ADC is still working. But what would happen if you have actually a physical disconnection between your source, your whatever, it could be a sensor or something, and your analog input? We have put this into an RX family, an RX device. It's what we call A to D input disconnect detection. And essentially what it does is, if there's a physical disconnection, electrical disconnection between the sensor, your input, and your analog pin, essentially you're floating. And depending on your system configuration, it may be looking like it's a floating, obviously it's a floating pin. It may look as a pull down or a pull up. Now, how can you tell whether now you do have a disconnect or not? So what we've done is we've integrated some circuit within the analog to digital block that would allow you to switch from your standard analog to digital sampling and conversion to what is we pull it up or pull it down by software or by this hardware to determine that you have whether a high or a low. So all of that it can be done automatically. So you see here the bottom diagram. Before your sampling starts, you can configure the A to D to switch to this self-testing mode, and you can tell it to either pull it up or pull it down, and then you can detect whether you do have a disconnect from your sensor. Memory protection unit. This is standard in the RX 200 and RX 600. Different levels of protection for reading, for writing, and for execution. Again, is this a feature that's called out anywhere in the specs? No, but this is something that can be utilized to protect those regions in memory from being overwritten, by whatever event that you may have in the system. Flash memory with ECC. This is part of all of the RL78 products. For every 32-bit of data that's stored in flash, there's 6-bit of error code correction that's built in. So every time you write to the program flash, this is happening in the background, completely transparent to the user. And when you're fetching, when you're reading from your flash, the original data is reconstructed through the decryption logic. So again, is this related to safety? Maybe, maybe not. It would definitely give you another level of reliability in your product. Similarly, RAM parity error check. RL78 has a feature that actually is inherent to the part. For every 8 bits of data, there is a parity bit that's stored, which can obviously detect whether you have a single bit error in your RAM. What else besides the products Renesas is working on? So we've worked very closely In Europe, so again, I'm talking specifically in this case about 60730. Europe is already requiring for all the appliance manufacturers to comply to this standard. So we work with companies like BDE to get certification of libraries for multiple products. And we have self-test libraries for CPU, ROM, clock, and so on. We support all of the main MCU families, RX 600, 700, RL78, and also the RAC microcontrollers.
So this is sample code that Renesas provides?
These are libraries, so they're in binary form. We can obviously provide the source code, but since they have been certified by a certification entity, obviously you can't really modify them. So UL 60730 is starting just now. Some of the there's been, I guess, some delays in really deploying this from the UL side. But I know that, or I heard that the 60730 from UL is going to start to be required starting in end of 2013 or 2014 timeframe. So all of the appliances that are being designed, and I'm sure, I know there's some appliance guys here, they may know better than me, but that's what I'm hearing from UL. So we're working currently with UL to do the same type of support. So we will have our libraries supported for 60730 by UL. But on top of that, one of the things that we are doing, which at least today I've not seen from anybody else in the industry, is we're taking some of these features that I showed earlier in RL78, some of those hardware blocks, and we're going through all of these FMEA analysis with UL so they can actually certify the hardware blocks. So in the end, you may have a combination of a hardware block that's been certified that you can use it in any way you want, as well as the libraries for some of these other testing. For other applications or other markets, such as industrial, 61508, our colleagues in Europe are working on a full, what we call safety compliance kit, IEC 61508. Initially, it'll be supporting the RX family. And again, it's the similar concept. It's going to be a TUV or TUF qualified libraries for SIL 2 and SIL 3 requirements. And all the documentation will be provided, and this is currently under development, available in Q1 of 2013. In addition to that, obviously, this is all this safety thing is a very very niche, very complex. So we do need to work with a lot of different partners. There's a lot of expertise in the field. We have to work with certification bodies. So you saw the examples of us working with VDE. Now we're working with UL, working with TUV. So we do have we are building this ecosystem to help you guys support in this whole safety requirement. So you can focus more on your own application and not have to worry about the safety compliance at a component level. In this case, the MCU. Okay, so summary. So there's definitely a growing need for higher safety. Different markets, different applications requiring a lot of standards coming out. There are different standards, but a lot of these methodologies to do self-testing are in many cases are very similar. So some of the techniques that or examples that I demonstrated can be applicable to any application. There's different ways to implement safety mechanisms. Going back to the same topic. So it's really application specific. And there's obviously a lot of things that Renesas is doing to help you design these safety compliance systems from a device standpoint, from a even documentation standpoint, libraries, certified libraries, development tools, partners, and so on. Any questions? Okay, so in closure, as I said, you as a designer, if you are doing your designs that have to comply to any type of safety standards, you do need to take a lot of this stuff into consideration. If you are already doing it and you have the experience to handle this, then you can definitely take advantage of the Renesas support, again, from a component level to a full infrastructure level. Thank you very much. We would appreciate your feedback. Thank you.